Well, thank you very much for the kind invitation. I'm quite honored to be here. Today I want to tell you about some of my research. This work that I present today is in collaboration with my former students, Sebastian Acosta and Leila Issa, my former postdoc, Ricardo Alonso, and longtime collaborators, Jocelyn Garnier from France and Chrysoula Tsonga, who's doing numerical simulations. So I will talk about wave imaging with sensor arrays. So this is basically an inverse problem for the wave equation. And the goal in these problems is to locate remote sources of waves or remote scatterers from waves measured at sensor arrays. So here I give two cartoons. The first problem is an inverse source problem, where we have an unknown source, which is shown here in red, which emits, this is the unknown source, this emits some signals, and then far away from the source we have an array of sensors. An array just means a collection of sensors which are close together, so they behave like a collective entity. And these sensors measure the waves, and from that, so these are usually time-resolved measurements, and from those we want to locate the source of waves. And in inverse scattering problems, now we have what we call an active array of sensors, where, which sensors emit some signals, so they probe a medium, and then they also record the echoes, and then from those measurements, the goal is to find scatterers in the medium. The two problems are actually connected because basically here, once the scatterers are illuminated, then they become sources of waves. So the inverse source problem is slightly, it's easier because it's an inverse, it's a linear inverse problem, but in any case, the two problems are connected. Okay, so these are the problems that we look at. And so how do we usually solve this problem? So there is a huge literature on imaging with sensor arrays, mostly applied literature. And the classic image formation is basically goes like this. So there are, of course, variations that involve all kinds of data processing and so on. But in general terms, what classic imaging is the following. So one takes the measurements at the array of sensors and time reverses them. Okay? So you record the measurements in time, and then you reverse them. And then you backpropagate these measurements to points at which you form an image. Now, this backpropagation is done with a model, of the best guess of how the waves propagate through the medium. So this is done with a mathematical model, of course, usually in software. And then the idea is here that if the propagation model, so the one that you use to backpropagate the waves to the points where you form the image, if this model is accurate, then what you will see is refocusing of the waves at the points in the support of the unknown sources or scatterers that you wish to find. Why this is so? It's basically the time reversibility of the wave equation. Okay, so it's like running a movie in reverse if you have the correct model. Now, we are interested in what we call imaging in complex environments. So what is complexity? So complexity arises due, for example, to numerous small inhomogeneities, or what is known as clutter, in the medium through which the waves propagate. Or complexity may arise due to rough boundaries. Now, this kind of complexity arises in applications such as non-destructive evaluation of structures, for example, aging concrete with ultrasound. So clutter there will consist of the many, many pebbles that you have in the concrete. They also arise in foliage and ground penetrating radar. So in foliage, the leaves in forest will be small inhomogeneities. It arises in seismic inversion, imaging in tunnels, imaging in shallow water. Okay. So the fact that we have complexity is quite a challenge in imaging. And the point here is that this complexity is basically a microscale feature of the environment through which the waves propagate. And these microscale features cannot possibly be known, and they cannot possibly be determined from the data that we measure, simply because we have band-limited data. And so this complexity is a source of uncertainty in the problem. So we have to live with this uncertainty. And so what is usually done in imaging is basically this complexity is mostly ignored under the assumption that, yes, it's there, but it just causes a small noise effect. So it's just like, you know, so people consider models and they say that the effect of the complexity in the medium is just some additive noise. And that is okay in some situations. However, in applications where we have waves that travel very deep in complex media, then this complexity cannot be ignored. And scattering that is due to this complexity is in fact a strong effect, and it's actually much more complicated than additive noise. Let me just mute for a second. Okay, so what we try to do in our study is we want to quantify this scattering effect, and we want to use what we understand from this analysis to devise robust imaging methodologies that mitigate this scattering effect. So in order to do so, what we do is we model the complexity, that is the uncertainty in the environment through which the waves propagate, with random processes. So what this means is that we place ourselves in a stochastic framework. And using this stochastic framework, we try to study the mapping of the uncertainty in the environment, which in the mathematical framework, that means that we have wave equation with random coefficients and random boundaries. And so we want to study the propagation of the uncertainty from this from the environment to the uncertainty in the wave field, which is what we measure at the sensors, and then finally to the uncertainty of the images that we construct. Okay, so now, so this is the stochastic framework. Now what is important to realize is that in imaging applications, we don't have much data. So what we have are just the measurements of the waves for a single complex environment. Okay, so in other words, we have only one realization of that environment. Okay, and so we don't have access to multiple realizations. And what we want is we want what we call robust imaging. It means that we want images which are basically insensitive to the scattering effects of the complex environment. Okay? So we want images that look essentially the same, independent of the realization of the random environment. And we only have one realization of, you know, the medium in which we measure. So that essentially means that what we mathematically want is an ergodic theory of imaging, which means that we obtain imaging functions that have the property of statistical stability or self-averaging that is achieved without ensemble averaging. So we seek for, you know, so we will construct images which sort of the fluctuations in the medium, the fluctuation effects average out by different mechanisms, such as integration over the bandwidth and so on. So we exploit the decorrelation of the waves over frequencies and so on. And then by superposition of uncorrelated quantities, we achieve averaging without using ensemble averaging. So that's the goal. Okay. So now, how do we set up such a study? Well, the setup is driven by applications. So, for example, if we study imaging of satellites, then we have a setup where the waves propagate in open space. If we study imaging in tunnels or in shallow water, then boundaries become important. Okay, so that's one, the domain is dependent on the application. And also, in these problems, there is a very important aspect of these problems which has to do with scaling. So what scaling means is that we need to know from the beginning what are the relations between the important scales in the problem. The scales are the distance of propagation of the waves, the wavelengths, the typical size of inhomogeneities, which is typically called correlation length, what is the standard deviation of the fluctuations, what is the bandwidth, and so on. So it's important to look at the scaling because in these wave propagation problems in complex media, there is basically not a universal regime where you see things. Okay? So depending on the regime, depending on the scaling in which you are going to see different phenomena. Okay? So it's very difficult to make general statements. So you have to look at different problems in a different setting. Now, I chose to talk here about imaging in complex environments arising in acoustic waveguides. So why did I choose that? Well, waveguides are important in applications, for example, in shallow water or in tunnels. But also, waveguides are a good way to see what are the important phenomena that arise in this problem. So essentially, they let us see most of the important effects with a very simple scaling. Okay, so this is one reason I decided to look at that. So I'm going to look at the simplest problem that one can see in waveguides, which is an inverse source problem. So we will look at what it takes to locate a source in a random waveguide. And I'm going to look at the problem in 2 dimensions. Actually, going from 2 dimensions to 3 dimensions adds some effects, and I will say about that at the end. Okay, so that's the problem that I want to talk about. So here is the setup of the model. So we have a schematic of the waveguide up there. We have a source which emits some signals. The wave is modeled by the acoustic wave equation, which is shown here. P is the acoustic pressure, which is what we measure at an array of sensors, which is far away from the source. So the waves propagate in the waveguide. Here I introduce a system of coordinates where this x with an arrow denotes the vector in the domain of the waveguide. The coordinate along which the waves propagate is called z, so that's typically known as the range direction. And the other coordinate, which is the depth in the waveguide, is called x, or cross range. Okay, so the waves are trapped by boundaries. So we take simple boundary conditions, which are known as pressure release boundary conditions, that is Dirichlet conditions, at the top and bottom of the waveguide. And the excitation comes from the unknown source, which is here in the right-hand side. And this source is modeled. So we say that the source is at the origin of the range coordinate, and it's modeled by some density rho. So we are really after the support of the source. And the source also emits some signal, which is modeled by a pulse, shown here. So this is the pulse. So this is how typically signals in imaging are modeled. So you have a pulse, F, with support, which is determined by 1 over b. So this b is known as the bandwidth. And then you have a modulation of a pulse by this oscillatory function, where omega 0 is known as the carrier or the central frequency. Okay, so that's the setup, that's the equation. And now you see that the waveguide has random boundaries, which this is the bottom boundary and this is the top boundary. And we also have a random medium, which we model with a random wave speed here. Okay, so here I took a very simple model. So the fluctuations are modeled by the random processes denoted by these mu's. And I'm going to assume that these are mean zero random processes, stationary in the range direction. I suppose that they are independent and mixing. What mixing means is that they don't have long-range correlation. And the autocorrelations of these processes are denoted by the script R's. Okay. And you see that here I introduced some scales already. So this little l is what is known as the correlation length, and this denotes the typical size of the inhomogeneities. Okay? And I chose the same correlation length. They don't have to be the same, they have to be similar, but I chose the same correlation length L here. And the correlation length is comparable with the wavelength, with the central wavelength, which is denoted by lambda 0. That is a regime in which the waves interact strongly with the complex environment. But the fluctuations, or the random fluctuations of the boundaries and the wave speed are small. And this we model with a small parameter epsilon. So this is a small dimensionless parameter epsilon. Okay? And so this is just to give you, to put it in an application framework. So now this is, I'm talking of course about an inverse source problem here, but suppose that we talk about an inverse scattering problem, like in the application of non-destructive evaluation of aging concrete. So you will have small fluctuations of the wave speed in the concrete, so that the small fluctuations due to the small pebbles in the concrete. And then you are after strong scatterers in the concrete that will be, for example, voids or cracks in the concrete. Okay, so that's basically the idea. Okay, so this is the equation that we want to study. And the first thing that we want to know is how does this uncertainty in the boundaries and the wave speed propagate to the field P, which is what we measure at the array. And then what do we do about constructing images that are insensitive to these fluctuations? Okay, so here is how we set up the problem. So first of all, what we do is we make a change of coordinates to flatten the boundary. So here is an assumption that the boundaries are, you know, the fluctuations are at least twice differentiable. And so after this change of coordinates, we obtain an equation which is a perturbation of the wave equation in what we call the unperturbed ideal waveguide. Okay? And so here, this is how the equation looks like. And I wrote the equation for z different than 0. So remember that the source lives at z is equal to 0, where we have some source condition. And now here we have a perturbation series for the operator. So the leading operator is this one, which is just the usual operator in the acoustic ideal waveguide. The next order, so this operator L1, is a partial differential equation operator that looks like this. And you see now that this operator has the random coefficients. So these are the fluctuations in the medium, and then the fluctuations of the boundaries. Okay, so this first order perturbation looks like that. So it's linear in the fluctuations. The second to the second order L2, we have a quadratic, again, a partial differential equation operator with quadratic coefficients in the fluctuations at the boundary. The fluctuations in the medium only appear in here. Okay, so we have a perturbation problem for the wave. And what we will do is we will use asymptotics to study the solution of this perturbed problem. And in order to see something, we will have to scale properly the range Z. That is, we have to look deep enough in the complex medium in order to see a scattering effect. Okay, so this is the setup. Okay, so how do we do it? Now, so the first thing that one does when one studies wave propagation in random media is one decomposes the wave. And the reason for that is because different components of the wave, you know, in general in open space that means a plane wave decomposition, so different components of the waves are affected differently by the random medium. So now the equivalent of plane wave decomposition in waveguides is what is known as mode decomposition. So this is how the wave field can be decomposed. And the modes are basically obtained by solving the unperturbed problem, that is the problem in the ideal waveguide, which is a problem that is very simple that can be solved with separation of variables. Okay? And so what are the modes? The modes are traveling waves and evanescent waves. And they are determined by these functions phi, okay, which are the eigenfunctions of the operator, of the differential operator in the cross-range direction. And so they are traveling waves with wave number beta j, which are defined here in terms of the depth of the waveguide. So this is the unperturbed depth. K here is what is known as the wave number. So we have a usual wave number and we have the modal wave numbers. And n is the number of propagating waves. So this is basically given by the ratio of the depth of the waveguide divided by half a wavelength. So we have propagating waves, as shown here in the first sum. The plus minus just means that we have waves that go to the right and to the left, so that is the forward and backward going waves. And the rest, so we have an infinitely many evanescent waves. Okay? So these are the modes. And the scattering effects and the source information are in the mode amplitudes, which are denoted by this AJ. Okay, so this is where the effects are. Okay, so now our goal is to, so this is the correct setup of the problem, and now our goal is to study these amplitudes. So now the first thing to ask is, you know, well, what are the scattering effects? How do they look like? So here I show you a numerical simulation. And in the top, we have a simulation for an ideal waveguide that is no fluctuations. And in the bottom, we have a simulation for a waveguide that is filled with a random medium. And so what do we see here? So let me just go back here to remember. So the wave is a superposition of modes. Okay? And here in what we measure, we're really looking at the traveling waves. And you see that, so we have these modes, these traveling waves, which propagate at different speed. Okay, so the waveguide is the dispersive, So the different modes propagate at different speeds. So the velocity, the group velocity for a mode J is given here. And you see that for the first indexes, for J is equal to 1, let's say, then the propagation, so this beta j is approximately equal to k, in which case, so the first modes propagate with about the speed in the open space. And then the later modes propagate much slower. So when j is close to n, then these modes are propagating, they're just crawling along, very slowly moving along the z direction. Okay, so here is what you measure. So this is how the signal looks like at one receiver in the array when you have a source which emits some pulse. So what this receiver is going to see is a signal like this, which is just a train of pulses. So this is the arrival of the many modes in the waveguide. Okay, so you can clearly see the pulses as they arrive. Now here is for the same source emitting the same signal at the same distance from the source to the array in a waveguide where we have a random medium. So this is how the signal looks like. It looks very noisy. And if you do this, of course, computationally you can do this. So if you do this experiment, this numerical simulation in many realizations of the random medium, and you take ensemble averages, then what you find is that the expectation of this field P is not at all like what you see in the ideal waveguide. So in other words, the effect of the random medium is not additive noise. It's much more complicated than that. Okay, so how do we study this? So the idea is, so you take the mode decomposition and you substitute that into the perturbed equation. Actually, you have to do it not with a second order equation like I showed it, but with a first order system. Okay. So you do that, and then you obtain a system of differential equations for the mode amplitudes. And these differential equations are driven by the random fluctuations. So, and they look like this. Okay, well, mostly. So let me just say. So we have actually infinitely many modes, right? We have the propagating waves and the evanescent ones. And then here what I did is actually one can show that it's possible to solve exactly for the evanescent modes in terms of the propagating ones, in which case we can write the problem for the mode amplitudes like this. So we have now a finite system of ODEs for the, so this A plus and A minus are vectors. A plus is the vector of n amplitudes for the waves going forward. A minus is the vector of n amplitudes for the waves going backward. And the system of ODEs looks like this. Okay, so we have the right-hand side, which is driven by the fluctuations. And this, you see the epsilon appearing and the matrix M, which matrix M, in fact, has a series expansion. And it's linear in the random fluctuations at leading order. Okay? And it depends, so it depends on the fluctuation processes mu, which model the complexity in the medium. And it also depends on Z. So they are oscillatory functions. So Z appears in a random phase, in a deterministic phase. Okay, so this is how these mode equations look like. And now, basically, what it takes to understand how the fluctuations in the medium translate into what we measure is basically to study this system of ODEs. And so the first thing that we need to see is how to scale. So at what distances should we look in order to see scattering effects? So clearly, you see here, we have the epsilon. And if we look at distances of order 1, and we look at the problem in the limit, so we're doing asymptotic, so we study the solution in the limit epsilon goes to 0, of course, we will not see anything. So the right scaling is what is known as the diffusion scaling. And it says that we are going to see a net scattering effect if the distance of propagation is of the order 1 over epsilon squared. And it has to be 1 over epsilon. So this is like a central limit theorem kind of a scaling. Okay. And so once we put this scaling, then the analysis of this solution is done with what is known as an averaging theorem or a diffusion limit theorem. And this is well understood for mixing processes like I consider here. Now, in order to be able to apply this theorem, you basically need to have an initial value problem. Now, so that means we have to look at the boundary conditions of these mode amplitudes. So the forward-going waves, A plus, we can specify what they are at z is equal to 0, that is the origin of range, which is where the source is, because we know suppose that we know the source, then we know the wave that is emitted. So we know the wave that leaves the source, okay? Now, for the backward waves, we don't know what comes back, because that depends on what it is in the medium, so we don't know what comes back at the source. But what we know is that we have a causality, so the wave equation is causal. So that means that if we have a finite time of observation, then there is a distance out there which is related to the finite time, where we know that we cannot sense anything that happens beyond that distance. So using this causality, we can set the backward-going waves, A minus, equal to 0, that distance. So we have now a two-point boundary value problem. We have initial conditions for the forward-going waves. We have end conditions for the backward-going waves. And we want to study this system in the limit epsilon goes to 0. In order to apply this averaging or diffusion limit theorem, we need to have what is known as an initial value problem, because this essentially what this theorem says is that the solution of the ODE that you study can only depend on the past, not on the future. Okay, so in order to do that correctly, you use a technique which is known as invariant embedding, which means that you work with translation, with reflection operators and transmission operators. Okay, so that's just a technicality. And essentially, when you do that, you find that in the typical regimes that we are interested in, that is for smooth autocorrelation functions, then, in fact, the forward and the backward going waves decouple in the limit epsilon goes to 0, which basically means that we can forget about the backward going waves, and this is something that is observed experimentally, for example, in underwater acoustics, and we deal with a forward scattering approximation. So from now on, we will proceed as if I only have the forward wave, A plus, okay? And then we can apply the diffusion limit theorem, and we can write what happens to our wave in the limit epsilon goes to 0. So here I write the result. So this is how the wave looks like. And this symbol tilde here means approximate for small epsilon in statistical distribution. So approximate, because you see I dropped the evanescent waves and I also made a forward scattering approximation. And in statistical distribution, so what do I have here? So you see I have the wave P, which is basically a superposition of modes again, or if you wish, this integral here is just a 1D wave, which is propagating along the z direction. And everything, so the source information, the scattering effect is encoded in this amplitude AJ, which is the limit of the forward amplitudes. And so I write it here this way. So this amplitude here, you see that's where the source information is. So this is the source density. And it appears here as the Fourier coefficient of the source and density, because it's the density integrated along these functions phi, which are just the trigonometric functions. And so you see the amplitudes depend on the initial condition. So this is how the amplitudes would be if I didn't have the fluctuations. But because of the fluctuations, the amplitudes are different, as modeled by this matrix here, P, which is known the propagator matrix. And this is a Markov diffusion, so this comes out of that diffusion theorem with known statistics. Okay? So this is it. This is the model of how the uncertainty in the complex medium propagates in the uncertainty in the data. Okay? So now we have a way of relating the source to the measurements through this random propagator. And we can compute all the moments we want. Okay, so let us look first at the coherent field. So the coherent field is the statistical expectation. This is what classic imaging relies on. So classic imaging or coherent imaging assumes that what you measure is basically the coherent wave plus small noise. Okay, so let's see what is the coherent wave. So here I show you how the expected coefficients, the expected amplitudes of the modes look like. And you see that the expectation of the mode amplitudes is equal to what the mode amplitudes will be. So AJ0 are the mode amplitudes in the absence of the complex environment. Okay? And then the complex environment introduces this exponential there. So there are two effects due to the scattering in the random environment that we see in the coherent field. The first one is a decay of the mean on a scale which is denoted here by Sj. So this is known as the scattering mean-free path. And here is how the scattering mean-free path looks like. So it has kind of a complicated expression, but it really depends just on the second-order statistics of the random fluctuations. So these are the autocorrelations. In fact, they are the Fourier transforms of the autocorrelations, which are, by definition, non-negative. So this is a positive quantity, so these are known as scattering mean-free paths, and they describe how the mean decays with range. And then we also have some anomalous phase, which occurs on some scale, which is, again, I didn't write it here, but it's similarly defined by the autocorrelation of the fluctuations. Okay, so the important thing to notice here is this decay of the coherent field, right, on the scattering mean-free paths. So what does this decay mean? This is a manifestation of randomization of the wave. Why? Because when you go to the second moments, so if you look at the second moments of the mode amplitudes, you see that they stay finite. They don't decay with range. That is simply because energy is conserved. Okay? So the mean goes to 0. The second moment stays the same. That means that the variance is large with respect to the mean. So that means that what you're really measuring is noise, random stuff. So it's just fluctuations. So that's what it means. So the decay is an effect of randomization. Okay, so what do we learn from this? So let's go back to coherent imaging methods. So the idea here is now so we would like to devise a robust imaging method, which, as I said, is, take the wave, time reverse it, send it back with a model, and then see how the image forms. So now we see that various components of the wave lose coherence on various scales. So the idea is, okay, in order to keep robustness, what we would like to do is to decompose the data over the modes. That just means projecting on these eigenfunctions phi. And then keep only the coherent modes, the ones that are not too random yet. Okay? And then throw away the others. Okay, so if we keep only the coherent modes, that is the ones that have large enough mean, then what happens is that you get something which is statistically stable. Why is that? Because if you look at second moments, and in particular at how the waves decorrelate over the frequencies, that is the decay of second moments of the field and the field computed at a different frequency, you are going to see that the waves decorrelate very fast at frequencies over frequency intervals of this order. So that means that if you have a bandwidth that is bigger than this epsilon square, okay, then that means that you are adding uncorrelated things, and just like in the law of large numbers, you are achieving self-averaging. So that's the idea, if the mean is large enough. So that's the idea. So that's what a natural idea is, to to basically filter out the random components of the wave, and then just do back propagation with the coherent ones. And it turns out that, in fact, you can determine what the coherent modes are, because in practice, you usually don't know these scales, right? So only the theory tells us you should do so. But in practice, you can determine which modes are coherent or not adaptively. So basically, you can construct an imaging function by weighting different components of the wave and searching for the best weights that give you a good image. So you need to have a figure of merit of the imaging function, which reflects essentially the trade-off between a good resolution. So good resolution means that you use basically as many modes as you can, because that gives you better focusing, and statistical stability, which means that you throw away as many modes as you need. Okay. So let me show you how this works. So I'm going to show two simulations. The first one is in a waveguide where we have a random boundary, no other randomness, so just the random boundary, and the next one will be in a waveguide with random medium. So here on the top, on the left, I plot the important scales. Ignore most of them except the blue curve, which is the curve that shows the scattering mean-free paths of different modes. So in this particular waveguide, we have 40 propagating modes, and j is equal to 1 corresponds to the waves that propagate faster, and j is equal to 40 to the waves that propagate very slow. In fact, I write here that if you really look at what these modes look like, they are nothing but a superposition of plane waves, as I write here. The wave vector for the waves is written here in terms of the waveguide wave number beta and the depth x. And you can see, so when j is equal to 1, so that is for the first mode, then this wave vector k is almost horizontal, right? It's almost in the z direction. So these are waves that are propagating in the waveguide. They propagate almost in the z direction, yes? They go, and then only once in a while, they meet the boundary where they reflect, right? Whereas, and so these are the waves that propagate fast. Now, the waves where j is close to n, they are the waves, so the wave vector there, in this case, so beta is very small, so the wave vector is almost vertical. Yeah, so these are the waves that go and they go like this, bang, 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 bang. Yeah, so they encounter the boundary a lot. Okay, and these waves randomize faster, right? Because over a short distance, they encounter the boundary many times, which is the only source of randomness. And that's what this plot shows. So this comes out of the analysis. So it shows that the first modes can travel a long distance, like 10 to the 4 wavelengths before they randomize, whereas the last modes, the ones that propagate slowly, they travel like, just a few wavelengths in z, and then they are random already. Okay. And this is how the result of this method that I showed you looks like here. So this is the image of a source. So we have a point source here, and the image, this is how the image looks like if you don't do anything, just classic imaging, okay? This is not, so the source here is at 100 wavelengths, so the result is not too bad because most of the modes are coherent here, okay? So you see some noise. Actually, it's hard to see in this picture. The peak of the image is here with slightly off the source, but it's not too bad. And here is how the image looks like if you use this adaptive figure of merit kind of a thing. You see the image is much cleaner, a little bit blurrier because we don't use all the modes. And what is interesting is the calculated weights using just numerical simulations, using this optimization adaptive thing, and comparing them with what the theory predicts. And you see that the theoretical and computational prediction is very good. And moreover, it agrees with what the picture there says. So it says if you image the source at 100 wavelengths, use only the first 20 modes, which corresponding to this picture says the scattering mean-free path of the first 20 modes is larger than the distance, which is 100 wavelengths. Okay? So that's basically what this picture says. Now, however, if you go in a random medium, so if you have, so now this simulation corresponds to waves propagating in a waveguide field with a random medium. The boundaries are flat, but the medium is random. And the source is actually closer to the array, so it's at only 50 wavelengths. So this is a strong random medium. This is how the image looks like. It's bad. And this is after the optimization. It is not good either. So the reason this doesn't work comes out of the theory again. So here is the plot of the scattering mean-free paths. So you see here, so we are trying to image at a distance that is about here. Okay? So at this distance, according to this plot, basically most modes are incoherent. And moreover, we don't have the strong dependence of the scattering mean-free path on the modes. So in other words, most of the modes, so the first 20 modes, they randomize almost on the same scale. So this mode filtering, which is, by the way, a very popular technique in the applied literature, doesn't really make sense in these waveguides. Okay. So in this case, the data that we measure is, incoherent. So coherent imaging is out. And so therefore, what we want to see is how we can still deal with such data. And so now we enter something which is called incoherent imaging, which is, so again, remember that what we're trying to do here is we are trying to obtain images or results that are self-averaging without doing ensemble averaging. So that is, we need some law of large numbers, and for that we need to work with statistical quantities whose expectation remains finite, doesn't go to 0. So the idea is to work with cross correlations. So this idea of imaging with cross correlations is something that has taken, it's just like a hot thing now in imaging. It arises in a variety of contexts, and here is how it looks like in waveguides. Okay, so first of all, in order to take advantage of these cross correlations, the first thing you need to do is you need to understand what is correlated and what is not correlated. I already showed you that, I already said that the waves decorrelate rapidly over the frequencies, so over frequency intervals of order epsilon squared. Now, what about the modes? So it turns out that if you look, the amplitudes of different modes are decorrelated. That makes sense because each mode corresponds to, like I said, these plane waves that take different paths in the random waveguide, and therefore they sample differently the random medium, so they are statistically uncorrelated. So the only thing that you can work with is what you call mode energies. So here is how that will work. So you take the wave that you measure, which is this P, and then you resolve it over the modes, approximately only, because in general you don't have an array that spans the whole depth of the waveguide, and that is represented by this indicator function. Okay, so you compute this Pj of t, which is a 1D wave, and then you take the intensity of this wave over a time interval, which is scaled by 1 over epsilon squared, and that has to do with the fact that the waves propagate a distance of order 1 over epsilon squared, so you need to wait that time to see things. And the window is modeled by this function psi. And because of decorrelation over the frequency, these things which are called the cross correlations, so Cj, turn out to be self-averaging. Okay? So what I mean, Cj is approximately equal to the expectation. It means that the variance of Cj is very small with respect to the mean. Okay? So we are basically dealing with deterministic quantities. Okay. So now what you want is you want to find the source. So what is it that we don't know? Well, we don't know the distance from the array to the source, which is this. That we don't know. And also we don't know the source density. So we want to locate the source, how far is it from the array and where is it in the waveguide. Okay, so now we can write the mathematical model. How we do that? Well, we use that C is approximately equal to the expectation, and the expectation we can calculate. And this is how it looks like, okay? And, well, here I introduce some matrices. So this beta is the diagonal matrix with the mode wave numbers. There is this matrix Q, which is just a coupling matrix due to the aperture of the array. If you are in a very fortunate situation that the array spans the whole waveguide, then this matrix Q is the identity. Okay, so you should think of it, Q is just like a coupling of the modes because of the aperture. It's not really important. You may think of it as the identity. And here is the window function that we have. And here is the stuff that comes from the statistics. So that is the second moment of the propagator matrix that comes out of that diffusion theory. Okay, so the unknown is the distance Z and the source density. And so now how do we find it? So we have the cross correlations for each mode. That is what we record and as a function of time. So first of all, to get the range Z, we look at time. So we look at arrival times. And this is something that is typically done in imaging. So we need the arrival time analysis of this integral. So this function here that I call big Psi, so that is a matrix. And if I didn't have the random medium, so if I didn't have the random medium, then this matrix gamma wouldn't be there, right? So gamma will just be 0. And so the energy, so this psi here will just be a diagonal matrix, which will be the window function evaluated at the time, at the travel time, corresponding to the speed of propagation of the jth mode, which is 1 over beta prime j. Okay, so this is the deterministic propagation in the ideal waveguide. Now, however, because of the randomness, so that introduces a difficulty in this propagation, which is manifested by this matrix gamma, which is here. So this is kind of like the discrete version of the radiative transport theory, really. And this matrix gamma is defined in terms of these autocorrelations, and it's a matrix which is of Perron-Frobenius type. Okay? So it's a matrix that has a one-dimensional null space, which is spanned by the eigenvector, which is just a vector with equal components. And then it has all the other eigenvalues negative, and that has to do with conservation of energy. So you can't, the eigenvalues cannot be positive because otherwise there will be just, energy will blow up, which of course doesn't make any sense. Okay, so the propagation now is no longer at the deterministic speeds because of this matrix gamma. Of course, the matrix gamma and beta don't commute. And so, in fact, you can actually do an arrival time analysis. This is, again, a scaling argument. So you can show that this guy here is a perturbation of this matrix gamma. And that means that you can actually calculate what this integral is using regular perturbation theory. And it says that so you see, so what you see here is a superposition of terms which decay with z, right? So the leading term corresponds to lambda is equal to 0, so that is in the null space, and the speed at which this component propagates is given here. So it's the harmonic average of the speeds, of the deterministic speeds, okay? And then different other components which decay faster and faster as the index j increases, propagate a different speed. Okay, so this is, you have an anomalous dispersion in the waveguide. And this is how it looks like. Okay, so how do we determine the range? Well, so we can use this information. So now we put that in the model. It looks like that. And then you see, okay, so in order to find the distance from the source to the array, we can just look at the peak time of the calculated cross correlations and compare them with what you get from the model. And this is a picture of how that looks like. So here I plot those CJs as a function of the mode index here. And then here is like time. Let's say it's actually depth, but let's say it's time. And what is important to know here is the following. So if I didn't have anomalous dispersion, so if I were in the random, in the ideal waveguide, the peaks, that is these reds, would all line up along this vertical axis, okay? However, because of the anomalous dispersion, you see this kind of a shape here. So this is a dispersion curve, and this is exactly what the theory says. And then by looking at this dispersion curve, you can search for, first of all, the distance z, that is the distance from the array to the source. And you can also search for the model of the fluctuation. So in this particular simulation, I have a simulation with a random medium. So we look for a parametric search of the autocorrelation. So we parameterize it in terms of the correlation length and the standard deviation. And here is, so we have some optimization, and here is a cross-section through the objective function. You see it's a very nice objective function. It's a convex function, and the reds correspond to predictions. And, so this is a very nice method of predicting the distance and also calculating the statistics, and in particular the gamma matrix that I had before. Okay, so this is the range estimation. Okay, this is the equivalent of travel time analysis in open space. Okay, so now once we have that, we now want to determine the cross range. So we know how far now the source is from us, but we want to know where exactly is in the waveguide depth. And this is hard. This is very hard now. So first of all, time doesn't help us anymore, so I'm going to integrate it out. And then I end up with this model of what I compute from the data. Okay, so this is what I compute from the data, and this is what the theory tells me it looks like. So why is this hard, right? So the source information, first of all, appears in here. And it doesn't appear as the density that I want to find. It appears as the absolute value of the Fourier coefficient. So even if I am very successful in determining this vector, okay, I cannot get so much about the density because only the absolute value of the Fourier coefficients. That allows me to determine some information about the source, such as the support, but I cannot find, of course, the whole density function. So that is one thing. Okay, so it's limited information. Moreover, finding this vector r is very hard because here, I just spelled out the matrix exponential, and what I have to do in order to find this vector r is to invert this matrix exponential. Okay, so these guys are decaying with z, right? And now I want to invert that. So that is an exponentially ill-posed problem, right? Because I'm trying to invert things that are decaying exponentially, so that is very hard. Okay, so that's what this says. And the best we can do is, for example, we do regularized inversion, and of course you can do all kinds of stuff if you have priors and so on. Here I don't do that. I just do the simplest that you can do, which is basically I do the truncated, I truncate, so I calculate the inversion, so it's an approximation, regularized inversion where I only sum over the components for which the exponential decay that I had in the previous slide wasn't too big. Okay, so that is the regularized inversion. And of course, now the question is, well, how good is this? How good is this Rj? How close is it to the true R? And the answer is, well, it depends. It depends how far you are in the medium. So if the depth is not, so in other words, if there are many components, J, for which this relation is true, then you actually do very well. You can actually get the first J components correctly. And that has to do with the structure of the matrix of eigenvectors. This is something that, of course, we prove, but here I just show you a picture. So this is how the matrix of eigenvectors looks like in the case of a medium, of a random medium. This is how it looks like if you have random boundaries. And you see that what is interesting is that it has sort of like a lower triangular structure. So if you truncate over here, you see the fact that you truncate over here for the first J's components is not going to make any difference because the components of the vectors that you would like to add are basically 0 in there. Okay? So you get a good approximation for the first J components. Okay. But however, if you go, so the deeper you go in the medium, the worse you are going to do. And in particular, when you reach a distance which is bigger, which is 1 over lambda 2, so that is the first eigenvalue of this transport matrix gamma, which is non-zero, this is known as the equipartition distance. So equipartition means that there is so much scattering in the waveguide that basically the waves really forget where they came from. And in fact, if you look at the data, how it looks like at such a distance, the data is nothing but an average of the Fourier coefficients, which is what you want to find with these weights. Okay? So this is now, of course, so what I showed you here is for a bandwidth which is not very large. It's large with respect to epsilon squared, but it's still small because I wanted to freeze the number of propagating waves. If you have a wider bandwidth, then you actually can do better because essentially for different regions in the band, you have different weights in these averages. And here is an illustration. So here is an estimation of a source where I use a bandwidth of, well, this is the bandwidth. And here is an estimation of a point source which was located here. And here is the objective function. You see it has some deep minima here, but then there's also a ghost. And that has to do with the fact that you only have the absolute value of the Fourier coefficients. So you can't really tell if the source is above the waveguide axis or below. That also has to do with the boundary conditions, but that's it. Okay, so let me summarize. So I just wanted to show you how sort of this kind of work goes. So we are interested in imaging with waves in complex media in regimes where actually the complexity of the media makes a huge difference. And mathematics can guide us through this process. It basically tells us, first of all, how the wave randomizes, so different components of the waves randomize in different ways. And it tells us how the waves decorrelate over frequencies, also over directions, because the decorrelation over waveguide modes is basically decorrelation over directions. And then we can use that in order to devise robust imaging methods. The best imaging that one can hope for is coherent imaging, which means that the waves don't go too deep in these complex environments. That is, there are significant number of components of the waves that are still coherent, in which case the results are very nice. If you are not in that situation, then you have to do what is known as incoherent imaging. Of course, there is a wide, like field, like diffusion tomography and so on that does this kind of stuff. But it's known that these methods are not very good resolution and they are very unstable. And of course, that showed up here. And now, of course, so now there are other things that one can add. So for example, 3D waveguides. So the fact that we only got the absolute value of the Fourier coefficients had to do with the fact that mode by mode, the waves decorrelate. Okay? However, if you have 3D waveguides, or for example, in electromagnetic waves, let's say in 3D waveguides, so you have modes that propagate with exactly the same speed, but there are many, many components that propagate with exactly the same speed. So in other words, if you look at the eigenvalue problem for the operator that you get here, you have degeneracies. So these degeneracies are basically polarization effects. And these polarization effects are important because they allow us to get phase information of the Fourier coefficient. So you actually can do much better than that. Okay, so I think I finished.
Thank you so much, Professor Borcea. We have time for a few questions.
Do you have any relation between the regularizing factor and the scale you use?
The regularizing factor in this last...
I do not know how you regularize, but
here,
apparently
here,
you use, yes. Okay.
Yes, so here the relation is this. So basically J is chosen in theory, because in practice you don't, I mean, you can calculate the scales once you know this matrix gamma, because everything is encoded in there. In other words, so it's basically something about the Fourier transform of the autocorrelation. But essentially, it's this. That's the relation. So it says that you want, okay, so, you know, you also have additive noise in the data, right, which I didn't put in. And that comes into effect in the regularization because you don't want to blow up things by more than something, okay? So you want to put a bound on how big these exponentials, because these are growing exponentials, are. So once you have that, then you know how big lambda j could be. Now, how big lambda j could be, you know, so once you know how big lambda j could be, you know, or you are at a distance z, right? You know z, so you know how big lambda j could be. And that tells you how big j could be because you know the matrix gamma, essentially. Yeah, so you can, but in practice, you don't really do it like that, you know, so that's why you do these adaptive things and so on. In practice, you don't, I find, like Professor said before, that you know, the models are very good to tell us what to do, but in practice, you should try to, you know, to sort of come up with methods that, you know, use the data a lot and, you know, adaptive estimation and so on, because it's not very safe to use very explicitly formulas in the inversion. Yeah, but the theory gives you that.
Thank you.
Other questions?